Good midday. Thanks. Hello. You guys know you have to show a little bit more enthusiasm in my talks. Hello. Actually, I should be the one cheering, because I was really, really nervous that nobody would show up to this talk. Because, you know, the title is like TCP UDP K. K in Spanish means like what? And it's not like a topic that is of much interest to people. So since you've all shown up, I'm thankful, and I want to say thank you before the next slide, which I'll tell you what this talk is about, and then you can all leave. Getting to that, what is this talk about? I will promise you that in this talk, there will be no mention of new JavaScript frameworks. There will be no there will be no talk about microservices, no REST. All of those will come in my talk tomorrow, which is the silver bullet syndrome. This talk is actually getting back to a little bit of basics. It's kind of like going back to school. It's the perfect talk that you can walk out and say, oh, I didn't learn anything new. I knew it all. Kind of like thumbs up, you're very smart. But it's kind of going back to explaining a little bit TCP UDP. What is the purpose of this talk? Well, first of all, for you to understand a little bit more about TCP UDP. Most likely, you will probably not end up using anything specifically from this talk, unless you're writing your own protocols. But I find that it is interesting to realize a little bit how things work under the covers, and then understand why some things are moving in certain directions. And I'll loop that back in with some of the aspects of HTTP, and in particular HTTP2. How many of you are using HTTP2 or have heard of it? So you'll understand a little bit why, also the reason for HTTP2. So I've given you a disclaimer. My only favor from you is now you don't walk out and you stay. Right? You can sleep, work, do whatever, just don't walk out. If you do walk out, still vote green. Okay, I'm serious. Right, the network, the ISO of the OSI layers. You're all familiar with this physical linked network, transport, session, presentation, application, and the vast majority of our life we've spent here. Right? Unless you're doing any kind of like socket programming or implementing protocols, a lot of the time that you're focusing on is spent on the application layer. Mostly, if you're doing HTTP programming, you're on the application layer, right? So all of the web frameworks, HTTP request response, all of that lives here. But if we go back down to this and we focus on several of these, we can see that each of these actually has a different function on top of that application layer. So the application layer you're all familiar with, HTTP, SMTP, POP, all of the IMAP, all of these protocols are implemented there. TCP UDP, that's the level below it. And that's kind of like the thing that is moving all of those packets back and forth, or the segments. Then we have the network layer, which is the IP, therefore TCP IP, the link, which routes the datagrams, and there's a misconception sometimes. UDP is user datagram, but datagram is actually what's on the link level, and then the physical levels that move the bits. So our focus today is mainly on the transport level. We're going to we'll look a little bit about HTTP, but we're going to try and focus a little bit more on the transport level. And when you start with communications, basically it's very simple. I have a server on one side, I have a client on the other side, I have an IP, everyone's familiar with IP, and the client talks to the server talks to the client. An IP address, you're all familiar with. It's composed of 4 billion addresses, and as of a few weeks ago, we officially ran out. Right? So there are no more public IP addresses. That's even despite NAT. The breakdown of our IP4 address, which really you don't have to know anything about except this part over here, the 32-bit source, 32-bit destination, and this data, which we'll get to, is that. Fantastic. Take a screenshot of it. Now, the next step is where we're going, which is IP version 6, which I kind of tried to fit in the same way with the binaries. Because you can't express it like that, we're going to have hexadecimal. And then there's notations. For example, if I want to skip the zeros, if there's a lot of blocks of zeros, I can just put colon, colon. So that's what we're going to get used to. Thank God for DNSs. We don't have to worry about that. The datagram itself has also been a little bit simplified. So now we've got 128-bit. And technically now, every grain of salt on the planet could have an IP address. So there is no limits to where we can take the Internet of Things, right? Anything you can think of in your house can now have an IP address, which is fantastic, because now we can get hacked from every side. Now, going back to this communication, of course, there isn't a one-to-one always. Like here I have a client, and then I have a 192 ending 242, and then I have a 245. But sometimes I actually have this 242, 242 on the same machine. Typical machines. We have web servers, SMTP servers, POP servers, all of those. And how is that kind of working? So this comes down to processes and sockets. I have processes on each point working with each other. And then each process is listening on a socket. So on the client side, I have this process called what they call multiplexing, which basically what it takes is all of the different processes and all of the different sockets, gathers that information, puts it on the wire, sends it to the other end, and the other end does what's called the demultiplexing, which deciphers that and allocates the exact packets to specific different endpoints, to the specific different services. And those services are pretty much uniquely identified by a port, which is what the socket is constituted of, right? So if we drill down to that data block that I showed you in the IP datagram, what we have here is that data is the gray part, and inside that we have a source port, we have a destination port, we have options, and then we have the actual message. So basically, a TCP UDP package is identified by a source IP address, a destination IP address, a source port, a destination port, etc. And that gray part, as I said, drills back down to that data aspect on the lower level of the IP4. Now, you already know that there's kind of pre-assigned port numbers. So you have the 0 to 1023, which are basically reserved by operating systems and well-known services. So 80 runs HTTP, 443 is SSL, etc. Then we have another block of ports which you can actually use for your applications, and you can register them with IANA. So if you go to the IANA list, there's actually application servers, Atlassian, all of these different ones have allocated ports. And then there's a block which is used for the client and server for dynamic port allocation, right? And that's the 49,152 to the 65,000. Hopefully we won't run out of ports. And TCP and UDP can actually work on the same port number, okay? And talking about TCP, UDP, those are the main two protocols that we actually have on the IP stack. And the difference of them is pretty much in this chart, right? So you have from one side, you have the heavyweight TCP, which provides you with connection orientation, provides you with reliability, ordering, data flow, handshaking, and we'll see what all of these are in a minute. Transfer mode basically means streams. It doesn't really have boundaries between messages. And then we have the UDP, which does nothing, right? UDP pretty much on top of IP adds very little. It just sends individual packets. And surprisingly, it's used quite frequently. So DNS is using UDP, DHCP is using UDP, TFTP, which is an unreliable FTP protocol, is using UDP. And it's actively used. But you know, a lot of focus has been on TCP. TCP, Transmission Control Protocol, RFC, 973. It's connection oriented. That means there's a virtual circuit. It basically, from an end-to-end point, there is a connection that's going on. It's reliable in that it makes sure that when a packet is sent, it arrives at the destination. It provides flow control. It's full duplex. That means communication goes on both ends. Messages are streams, as I said, so there's no real boundaries, but it's also heavyweight. And to give you an example, this is a Wireshark. How many of you use Wireshark? Okay, so this is Wireshark, and this is a simple echo server. All I do is send a hello, and I get a hello back. Look at all the packets that are going through, right? I have a bunch of packets at the top, then I have a few packets that is actually the hello, and then I have a bunch of packets at the bottom. And all of that for a simple hello. But all of that is required because of the way TCP is built. But all of that also impacts our applications, and we'll see why. So to start with, we have the handshake, right? TCP has a handshake to basically synchronize the client with the server to make sure that moving forward, anything we do goes well, right? It's reliable, ordered, etc. I don't know, in Belgium you don't have it. In Holland you have the 3 kisses kind of thing, right? In Spain we have 2 kisses, in Holland they have the 3 kisses, kind of the same thing. So here when I want to speak to someone, I first do send the sync. That's the client, that's the server. I send the sync, then I receive and acknowledge, the acknowledge comes back, and then it goes back. So the client sends the sync, the server sends the sync, acknowledge, goes back and forth, and I do that 3-way handshake. So if we look at this big interchange, you can see that there at the top, all I'm doing first is this 3-way handshake. And what that's providing is a sequence number, you can see. Now the sequence number is actually random. So it can be any number. It can start at 56,294, right? The important thing is that from that point on, it starts to increment by the number of bytes that are being sent in the payload and by the 3-way handshake initialization. What Wireshark does by default is basically set that to 0. But you can actually switch that option off in Wireshark and say, just show me the real number. So every time I open a TCP connection, what it's going to do is do a 3-way handshake. And once it does that 3-way handshake, then it starts to actually send information. Sometimes it also does this thing called the TCP window update, which we'll get to in a moment. And then it starts to send this information back and forth with this sync, ACK, sync, ACK, sync, ACK, which we'll see as well. And that just goes on until it gets to the end, and then it tears it down. And it kind of does a 3-way handshake for tearing down the connection as well. Kind of like saying, I know that from this point on, there's no more data coming in. Okay? So if we take a look at a segment in detail, you can see this is each of those packets. You can see that there's basically a set of flags which are saying what's going through. So I have a different set of flags, and I have the acknowledgement flag, I have the sync flag, I have the push flag, reset flag, etc. And this is communicating what packets correspond to and what's coming back and forth. And what makes TCP reliable? How does it actually implement reliability? So this is a one-way. Imagine that this is a single direction. We'll see how it does it in full duplex. If you were to do a naive implementation of reliability, what you could do is you can send a sequence of packets. So here I say I set my sequence number to 1 and I send 2 bytes. The server now acknowledges and says, okay, I've received 3 bytes. So it sends back the sequence number plus the number of bytes it's received. So sequence number was 1. Received 2 bytes, sends back 3. Now the client now sends the sequence number that it has plus new bytes. So in this case, 8, and the server would send back acknowledgement 11. Right? And this is a single-way reliability implementation in TCP, basically. Every time I send the packet, I'm going to acknowledge the bytes I've received and send that back. Now, since TCP is full duplex, it's trying to do this in both directions. And the way it does it is pretty much similar, but it piggybacks off of the data that it's sending back. And you can see the sequence and acknowledgements are inverting their role. So here I have the same client and server, and then I have a sequence 1, acknowledgement 10, for instance. I send 2 bytes. So now the acknowledgement comes back as 3, the sequence comes back as 10, right? And then I send 4 bytes. So now the sequence comes back as 7, because 4 plus the previous 3 is 7. The acknowledgement comes back at 12. So this way, it's allowing to do full duplex, bidirectional, reliable communication. And to not make the overhead higher of each data send back and acknowledge, what it does is use piggybacking. So basically, on the data load, it's sending back the acknowledgement. So if you see that, for instance, again in the diagram, you can see that there is the push, the push I'll get to, the ACK sync going back and forth in both directions. And what is this push? Because this PSH appears quite often. So this is actually a screenshot of Telnet, right? This is a Telnet application. I've done a sniffing. And what you can see here is that every time I basically type a character, it's sending it through, and it's sending this push flag. And what the push flag is basically saying is push that up to the higher level, right? So as a Telnet application, when I want to type something, I want to make sure that the receiving end is basically seeing that, and it's not seeing it in chunks of data. So what it does is basically push that value up to the upper level, in this case, the application level that takes care of it. So that's what the push exactly stands for. But you can see that in certain cases, that's not recommendable, because sometimes I don't want to constantly send back exactly what I have. I want to let the buffer fill up and then send back. For instance, if I'm sending back a stream of data, a file or whatever, I don't want to continuously have that push. So you can also, the TCP is capable of doing that as well. In this sequence, you see that I'm streaming a file. So you can see that there's a lot of acknowledgements, and then there's only a single push when a certain amount of buffer has been filled up. Okay? Now, that's in terms of reliability, but there are other aspects that come into problems with the network. One of them is flow control and congestion. So if I have one server here and I have one client here, and these two machines are talking, I can basically say, okay, I can send you 100 bytes, and this 100 bytes goes from the client to the server. Great. The server can do the processing. It's fantastic. And then I say, okay, 100 bytes you can cope with. Let's try and send 500 bytes. Okay, 500 bytes I can cope with. At some point, what happens, though, is that the server can maybe not cope with the processing. And when that happens, it starts to drop bytes, because it says, I can't cope with this. So the buffer fills up and it starts to drop bytes. If that happens, since TCP is a reliable protocol, what it has to do is, again, send the same bytes. In order to prevent that, there's a thing called flow control, which basically allows you to adjust exact amount of bytes you want to send over without losing bytes and without congesting the other end. And that's when I have the situation of two machines, point to point. If you look at the internet, between the internet we have, like, if I want to talk to a server that's way over there in the US, for instance, I have routers, switches, NAT, all bunch of things in between, and each of these have their own implementations of IP. Each of them have their own buffer implementations. All of these are going to affect the flow of information going back and forth. So that's where the Nagel algorithm that you've heard of comes in, which is basically allowing you to control the flow of information. And what's that done? That's done by basically saying Windows update. So I set a window update and I say that's basically the buffer size, that's the amount of information I can send. If I see that things are going well, then I start to increment that window and increase the size. And that's what is called in TCP slow start. So slow start starts with a single window, a small window, and gradually it starts to increment the size of the window. Okay? Now, of course, that is great, but at the same time, it has problems, because we know that every time I start a TCP connection, if I want to stream a lot of data, for example, it's going to still start slow. But it's okay. If I'm streaming a file, it's fine, because eventually it'll get to that optimum point, and then it'll start to stream that file nicely. But take a look at, for example, a typical protocol on which we use TCP, which is HTTP. HTTP has a lot of small requests for files. And each of these, think about it so far. What is it doing? It's doing a handshake, it's establishing a connection, it's doing a three-way handshake, it's sending a whole bunch of acknowledgements for reliability, it's setting a window update, and it's finishing. So look at the overhead that TCP is adding to HTTP. Right? In addition, TCP gives us one other thing which is fantastic, but also contributes negatively to HTTP, which is head-of-line blocking. Which basically means if I want to make sure that the upper application level doesn't have to worry about packets coming in out of sync, out of order, I got to take care of that. And that effectively means that if one packet is lost, I can't continue. I got to wait until that packet is sent again and then continue, right? And that negatively impacts HTTP. So you're all familiar with the concept of bandwidth and latency, right? Yes? Bandwidth is how wide my street is. Latency is where I have to go, right? So, if I got to run 12 kilometers, well, drive 12, I never run, 12 kilometers. Right? So latency is limited by what? Speed of sound? No, That was a trick question. No, it's limited by speed of light. And until someone breaks that, latency is basically limited by speed of light. So that means that the fastest I can go in an optimum vacuum is how fast light can go over a fiber optics line, right? Now, we don't have that vacuum. And when we're going from one point to another point, there could be thousands of factors in between. What does that translate in? In that if I'm, for example, here in Belgium and I want to ping somewhere in the US, it can take up to 200 milliseconds, right? Now, before I continue, I want a moment of silence and I want that to sink in. It will take 200 milliseconds to travel 8,000 kilometers. Okay? Sunk in? Okay, great. Apparently, that's an issue, right? That's why people are complaining that, you know, if I go to a website and it takes more than 1 second for me to get my products, I won't use that website and I'll go to the competitor, right? Do you do that? Does that happen to you? In Spain, I don't do that because I have no choice, right? It's slow and there's only one person that sells. But realistically, we have reached that point where for us 200 milliseconds is too slow. Well, okay. But the issue with that isn't the bandwidth. The issue is the latency. If you take a look at the HTTP protocol, what that is doing is every time a typical website is creating multiple requests to multiple different resources. Each of those requests are traveling on TCP. Each of those TCP connections is opening up a new connection. It's doing the three-way handshake. It's implementing reliability, flow control, all of these things. It's closing the connection, right? All of that adds issues. It adds latency because I have hundreds of different connections going out. Here's a chart which basically shows you bandwidth versus latency on page load times on HTTP. You can see that at some point, it doesn't matter how much bandwidth I have, it's not going to impact the speed and load time. Right? If you take a typical look at an HTTP connection, you can see that the breakdown is queuing, DNS lookup, request sent, and here you can see that the content downloaded is 0.84 milliseconds, and the overall time is 355 milliseconds. Now, again, this is at the HTTP level. Right? Take a typical web page and you get the waterfall diagram. How many of you use this site? It's called Web Page Test, which is fantastic. It goes and it shows you all of the waterfall of loading of the application, of the web page, and then the cached version, etc. And you can see this waterfall effect. And all of this is consequence of TCP. It's consequence of head-of-line blocking, it's consequence of three-way handshake, it's consequence of the implementation of reliability. All of these are contributing to the slow response times. And what HTTP2 provides, and what Speedy provided, which is what HTTP2 is built on, is ways to overcome this by creating a multiplex stream, which basically means now I have a single connections, which means I no longer have to open up multiple connections, etc. So to summarize, HTTP2 is about performance. But it's about performance trying to overcome the limitations of TCP, not HTTP 1.x protocol. Because semantically, HTTP2 is basically the same as HTTP 1. There's no difference in the semantics. It's still get, post, push, etc. Well, there's a server push, but in terms of verbs, headers, bodies, all of those are the same. The focus of HTTP2 has been about trying to improve the performance because of the underlying issues of TCP. Because TCP was never built for HTTP. Okay? So now you know why HTTP2. And by the way, who's using HTTP2? Nobody. Who's using Twitter? So you're using HTTP2. A lot of sites are actually using HTTP2. Under the covers, obviously. The difference between Speedy, which is now being deprecated, and HTTP2 is that HTTP2 opens up a whole new world for us. Because at the same time that it fixes these issues, it provides flow control, flow control and thus server window regulation, priorities, all of this, it brings it up a level and gives us an API in order to play with it. Effectively meaning in 3 years, we'll probably have talks at conferences saying how to not shoot yourself in the foot with HTTP2. because we're very good at that. Okay, so that's what TCP is. Those are some of the issues that TCP have. And working with TCP, how many of you actually make socket connections, like socket, work directly with sockets? Okay, for those of you that don't, I'll show you very quick, couple of quick samples. It's very, very simple. So here I have, you can see my screen, I can see it there. Let me take my mouse over. So here I have, it's very simple, right? So I create a server socket. Here what I'm doing is basically creating, actually let's start with something very simple over here, a discard server. And basically a discard server is the simplest implementation of a protocol. I send it something and it ignores me, kind of like my children. And server socket, I set a port, I set the number of connections it's going to accept, or the number of connections it's going to queue, and I'll tell you that in a second. The address binding, if I want to bind it to a specific port, because IP, because remember, you can have multiple sockets open on the same port, but on different IPs, on the same physical machine. And then what I do is I basically say, now accept connections. When a telnet connects to that, it's going to return a socket connection, and then I'm going to just process that socket connection. And here what I'm doing is just reading the input, checking to see if it's not a black line. If it is, if it isn't, I'll read the line and do nothing, pretty much. Okay? If we go back here, what happens is that basically if you run this, this is going to accept a single connection. As soon as the telnet closes, it's going to die. Very, very, very pointless and useless. And that's not how you do it in production. So here is a single run single server. So what this is doing is basically an echo. Now I send it a message and it just sends the message back. But again, the problem here is that if you run this, it's going to accept a single connection and it's going to process that client. So again, this is not what you do. Normally what you do when you set up a TCP server is you provide a threaded model. So basically, every socket has its own thread, which is, in this case, over here, which is exactly the same as the previous example. The only difference is that I'm launching this process client in its own thread. So now I allocate a thread to a specific client, and it goes off and handles that connection, right? And that is absolutely fantastic, and it's great. And the accept header here tells me how many connections I can queue, basically. So the accept header. The accept call is queuing X number of connections, which is defined on the server socket here. So what that means is that if 300 clients try and connect, it's not going to let them. If 10 connect, it's going to let them. The 11th one is going to drop until one of the clients disappear. So it allows you to queue up connections. Now that has also its issues, right? If we go back here, you have this thing that a lot of people have been talking about, which is threading versus event loops. Now, how many of you are familiar with Node.js? Right. So in a typical threaded model, which I've just shown you, basically get a request, and then what happens is that you get a bunch of threads, and each thread is basically handling that request. Okay? So the thread is coming in, I'm allocating that client to that thread, I go off and I do my stuff. This is a typical threaded model. In an event loop model, what I have is something a little bit different. What I have here is an event loop that requests are coming in. So it's a single loop. It's a single threaded model in a sense. It's just looping over, getting new requests, and then it's delegating long-running requests to what is called worker threads. The worker threads go off and do the work, and then when the work is done, it does a callback. This is typical Node.js. And there's a common misconception in that this is single-threaded. It's not. It's not magic. The difference is that it's delegating that threading work outside of your scope. So it's handling all the NIO, all the I/O in a non-async way, etc. Right? Node.js kind of implements that. Charts that show you comparisons, which always favor the person producing the chart, show you that like Nginx versus Apache that uses the threaded model, right? So the number of requests per second versus the concurrent connections that you can get. And then if you do performance comparisons in terms of memory, it also shows you that, well, this is actually much more effective because you're letting the underlying framework, library, whatever you're using, handle the actual threading model for you. If you're in Java, don't worry. You don't have to go to Node.js to take advantage of this. There's another technology in Java called Nettie, which basically does the same thing, right? The difference is that, of course, when you use something like Nettie, the programming model is somewhat different. So here I have a single TCP server. Setting Nettie up is the best thing to do is just like collapse that, and then that's you set up once. But basically, I'm running events. So it's more like an event model. I just read, write, do whatever, connect, disconnect. So pretty much when you're doing Nettie programming in Java, you're going to be implementing different event handlers. Okay? But that takes care of the NIO under the covers and all of the threading. So that's a little bit in terms of TCP, and of course protocols that are built on top of TCP. So you have HTTP 1.1, which is very simple. It's a text protocol, request, response. HTTP 2 is, by the way, binary. It's not text. And if you're wondering how binary protocol works on top of text protocol, it's called TLS, right? So it's basically creating a point-to-point, and it's using TLS to provide this compatibility in a sense. It can work with non-TLS, but by default, basically, everyone's going to be using TLS. So that's a typical example of HTTP. IMAP, very simple. It's all based on text. The server says, OK, IMAP server version 1.1. You send the text login, user pass, it responds. You parse that response. You send more information. You parse that response. And most of the protocols nowadays that we're using, POP, IMAP, SMTP, all of those are text-based protocols. Now, you can obviously roll your own. And in fact, in my past life, when I was young, I implemented a bunch of these protocols, and I also rolled my own protocols. And it was fantastic because you just created this text protocol that only you and whoever was talking to you needed to know, and you rolled your own. You don't necessarily have to build on top of HTTP. If you want a very simple protocol, you can just do a text-based protocol and get rid of the overhead of HTTP. However, I would recommend nowadays that if you really treat HTTP as what it is, which is an application protocol, it's worth probably building on top of that, whether or not you do REST. So first of all, make sure, obviously, your protocol doesn't exist. Define it unambiguously between the two parties. And text is very simple, but at the same time, it's very hard, because text protocols aren't easiest to parse or efficient to parse as binary protocols. Right? You can have a lot of bad characters in there, then you have the base encoding. If you want to send binary, you've got a base 64 encoded, etc. So it's not the easiest thing in the world either. So what are the benefits of TCP? It provides you a reliable connection, it has low overhead over higher level protocols, and it provides you with a persistent connection. So when to use it? And I've put a little star in terms of reliability is crucial. Right? Because you don't need TCP for reliability. You can actually create reliable protocols using UDP. But TCP reliability isn't simple, and the algorithms implemented aren't simple. So don't reinvent the wheel. In essence, if UDP, which we'll see in a minute, if you want to go full-blown and start to create your own reliable protocol on UDP, really consider what value you're adding over what's already available on TCP. But you have to take into account all of the overhead that TCP is adding. And of course, have this concept of a connection. Do I need a persistent connection? Do I need a long-living connection? Because HTTP is a typical example where the protocol wasn't effectively well built on top of TCP. And in fact, it was only until HTTP 1.0 when we had persistent connections did we gain some performance. Because up to 0.9 HTTP, every request opened and closed the TCP connection. Right. So it was in 1.0 and then it was backported, sorry, 1.1 and backported to 1.0. UDP, the forgotten kid. User datagram protocol. Again, RFC, go look it up, read it, fantastic read, bedtime reading. Connectionless. So if you don't want connection, that's your thing. There's no reliability, there's no ordering, there's no congestion control, but it's lightweight. So it takes everything away and it says, here, you don't get anything, but I'm really fast. If you take a look at a message, here is basically that same echo server, right? I send a hello, I get back hello. 2 packets. Okay, 2 packets. The packets, however, contain something important, which is the actual endpoint, the client endpoint, server endpoint, are all self-contained in that packet. So what that means is that when I send the packet from a client to the server receives that packet, but there's no connection. Therefore, how does it know where to go? How does it know if it needs to respond, how to respond? That information is contained in the actual packet, right? So it has the source IP and the source port, and it knows how to send information back. But it's part of a different datagram packet. The difference, of course, here is that if that data packet is lost, well, it's gone. I don't know anything about it. So if you take a look at some code here, we can see that this is a simple time server. You can easily identify what's happening here. So I create a datagram socket, which is the equivalent of a UDP packet, and I basically assign it a buffer, etc. And then I read some data here, and then from that data, from that packet that's coming in, I actually get the address and the port. And that is what I use to, if I want to respond to that request. Right? So under the covers, you need to now get access to the port and IP, because you no longer have this connection that's been open and you can just send back and forth packets. Each one is its own independent request response kind of thing. Now, before I explain one broadcast, everyone's familiar with networks and subnets, right? So I've got a network, which is the first 3 blocks, and then I've got the host, and then I have the subnets versus the network, and then you can get the subnet mask by bitwising the AND that gives you the network with the host. And what this basically means is that if I have 2 blocks of machines, if I have a bunch of machines on this side on the network 192.168.3.x, and then I have 192.168.5.x, these are on 2 different networks. And in between I have a router or a router. And what the router does is route packets between different networks. So there's one problem right now is that, first of all, most routers implement NAT, right? Network address translations, which basically allows a single company, for instance, not to have, all of us don't necessarily need to have a public IP address, given that the public IP addresses are limited. We had NAT, which kind of resolved it. Now, NAT works fine with TCP. With UDP, though, there's a problem, because there is no virtual circuit. So how the hell do I know when to open a connection, when to close a connection, when is it done? And there's techniques and algorithms that kind of implement that. But basically, to boil it down, all routers contain a UDP address translation, which basically is a temporary table that maps incoming and outgoing UDP packets and holds on to them for a while so that it knows how to route it to a proper machine inside a network. Now, sometimes UDP, what's very good for is the ability to broadcast. So with TCP, what I'm doing is I'm creating a point-to-point connection. UDP is very useful for when I want to do a broadcast. For example, I want to broadcast messages to all the hosts within a single network. And that's what UDP is very good for, which is called broadcasting. Now, the problem is that broadcasting won't work across routers, right? So you can't really get that to work across routers. The broadcast address is basically a bitwise OR of a bit complement of subnet mask and IP, which basically means that I send it to the, if that's my network, that's the net mask, the broadcast address is .255. And that effectively means that anyone on that network can potentially receive that UDP packet, and we'll see when you can use these things. Multicasting, that's somewhat different to broadcasting in that I can have nodes having to subscribe to a specific point, and then that point kind of broadcasting things out. So this can cross network borders, and it's very good for low bandwidth, high demand basically video streaming. So basically what it does, you stream to a single machine and that multicasts it out to multiple machines. Something, again, you can use UDP for. Now, what are the benefits of UDP? Lower overhead. I have 8 bytes versus 20 bytes, basically. No connection makes it much faster. I don't have the 3-way handshake to set up. I don't have the 3-way handshake to tear down. Not having reliability makes it faster. I don't have to acknowledge all packets. However, I lose the reliability, right? Which effectively means that if I want to use UDP, I have to provide you reliability at the application level. Which means that if I want a reliable system, I need to implement it myself. So I gain the fastness, but I lose reliability. Now, having said that, UDP is commonly used. In fact, for instance, in the stock market, a lot of financial companies use UDP to broadcast the stock prices, etc. Why? Because maybe a loss of one packet doesn't really matter because the next one is going to come 1 millisecond after. So you really have to equate the balance of if it's okay for me to lose a packet. What you shouldn't really do is say, you know what, I'm going to reinvent TCP on top of UDP, because most likely you'll end up with a slower protocol than you would if you just use TCP out of the box. When to use it? When speed over reliability is required. And again, a little star because it can be somewhat reliable. If you're streaming video and you lose 5 packets, no one's going to notice. It's not going to notice. So video and audio streaming, self-contained kind of protocols that are like simple packages coming back and forth, and discovery services. Very typical application use of this is, for example, licensing servers. Most licensing servers send out UDP packages to find out, you know, what applications are on the network, which ones are, you know, what applications are instantiated, what are being used, etc. When you don't know who to contact, if you want to contact a server but you don't know the IP address, you can use broadcasting to kind of make that discoverable on the actual network. So what else? When you're doing this kind of thing, there's a whole bunch of tools which are very, very useful. Wireshark, and if you're on OS X, now in 1.99, it's no longer required to have X11 and Quartz. You can just launch it up and it works. And it's got somewhat of a nicer interface. So Wireshark is fantastic. It's also very beneficial if you're doing any kind of, if you start to look at HTTP2, Wireshark works well with that. It already has support for HTTP2. And it basically works the same way as when you're trying to use Wireshark with TLS. You just point it to an SSL keylog. There's blog posts and instructions on how to send this up on the Wireshark. But you can use that for HTTP2. Other tools are, obviously, there's Telnet for any kind of text protocol. Is a very good client when you want to basically test your server implementations, because it's the chicken and egg problem, right? Which one do I implement first, the server protocol or the client protocol? Server, and then test with the Telnet, and then do the client. NC, which is kind of like Telnet for UDP, netstat and route, which allows you to examine connections and routing information. Postman, Fiddler, if you're using IntelliJ or any of our tools, you've basically got a test RESTful web service, which allows you to also do any kind of testing for HTTP protocols, and Nagios for monitoring, etc. So to summarize, basically abstractions are good, and it's really great that pretty much we don't have to deal with any of this, really. Most of the work that we're doing is basically at the application level. Most of our web applications right now, whether we're doing actual web user interfaces or we're doing endpoints, they're all built on HTTP. However, I find that it really does provide value to understand what is going on under the covers, and when does it make sense to optimize, when does it make sense to tweak things. Okay. In fact, if you look at, as web developers, if you are web developers, you've done a whole bunch of optimizations in your life, right? You've done domain sharding to open up multiple connections to try and get page load times faster. You've done script concatenations. You've done what is that other thing? Spriting. How many are familiar with spriting, right? Which is basically before you had a single image, now you have one big image that contains all of your images, and then you spend a good 6 days trying to use CSS to tweak it and place the exact images. All of these are done not because of the shortcomings of HTTP as much as the shortcomings of the underlying protocol, which is TCP. Right? And why? Because of all of these things that are going on under the covers. Fortunately, with HTTP2, a lot of these issues are resolved. Unfortunately for you, all of the optimizations that you have done, you're going to basically have to undo. Okay? But it's good. It keeps us in business, right? So really, you know, it's more, this session was more about just understanding a little bit what's under the covers. And of course, if you're doing any kind of TCP programming or socket programming, know that you've got extensive APIs available on the JVM, and Nettie especially is very good. And I said I want to mention microservices, but you can use this for microservices too. Okay? So thank you.